Hello everyone, welcome to this video. My name is Emerson Ahari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you an example for flood detection using SAR data and precipitation together. Compared to the previous flood detection tutorial on my YouTube channel, in this tutorial, I'm going to show you an example about the flood using precipitation and SAR data together, because one of the main important factors in the flood detection is precipitation that should be considered in the flood detection studies. And this study also, or this example, includes urban flood detection using SAR data that is very beneficial for the users who are working on urban floods. So in the first step, you need to select an urban area that is affected by flash flood over the last years. As I searched on the net, I found that in January 2020 in the Jakarta, and we experienced a flash flood in this region, and lots of area covered by the water bodies after the flood because of the heavy rainfall at the late of December 2019 and early January of 2020. And now there are a lot of references on the net. If you search about the Jakarta flash floods, definitely you will find a lot of examples and articles about these flood events. And now I'm gonna show you an example how we can detect such kind of floods happening in the urban area using SAR data, and how we can monitor or measure the precipitation before and after flood events. So let's go to the code editor environment, and in the first step we need to find a study area using search places and dataset on Google Map available here. Just type about the Jakarta or region of interest. As you can see, the Jakarta is capital of Indonesia, and it is one big city area, and then you can see its extent here. In the satellite view, you can a better understanding, you can have a better view about the location and land covers available here. So now I'm gonna select the urban area using drawing tools available here. I'm drawing a rectangle to select the part of a city here, for example, just like that. This is the region of the city. Actually, in this area, most of urban structures considered, because I'm gonna detect the flooded area with a good accuracy. That's why I need to have a good extent for the good extent using drawing tools available here. After region of interest selected, using map.center object geometry, you can have access to the region of interest whenever code is running. For example, now if I run the code, after a few moments you will have focus on a study area due to the map center object. In the next step, we need to call SAR or synthetic aperture radar from Sentinel-1 satellite. Now I'm making a SAR data. This is SAR for before flood event equals to. Now go to the search places and dataset, and here you can call or you can go through the Sentinel-1 data, searching on the database, and Sentinel-1 a GRD product is available. Import it into the code, and now let's go for the next part of the code, and then we will back to the Google Map for the further visualization. So SAR for before this, now I'm gonna call SAR data for the days before the actually flood events. So first, image collection assigning to the SAR before, and then using filter date, we can choose the period of time just before flash flood or the flood occurs. So here, as you can see on the net, or if you search on the net, you can see that because of the heavy precipitation starting from December, late of December, and ends to the January, early of January, flash flood occurred. Now we can choose a period of time before late of December, for example, from 20 to 25, a couple of days or a week before the event. So now here 2019 December, and for example from 20 to 27 could be a good period of time as an indicator for before flood events. Just we need couple of images before flash flood to compare it with after flood images to show that how flooded area actually reflected in the satellite data. So 2019 and 2019, and the end date will be 2019 December 28 or 29 even. So that filter bound, you can bound your data to the region of interest that here is as a geometry. When you are dealing with the synthetic aperture radar or Sentinel-1 data, we need couple of filters, couple of extra filters that are specifically used for the Sentinel-1. Now I need to call those of data in which transmitter-receiver polarization equals to VV. Now I need to call the data Earth engine filter list using that list contain. I can call those of Sentinel-1 data in which transmitter receiver polarization is equal to vertical, the direction of actually radiations going toward the target, and the direction of electromagnetic radiation back toward the satellites. Both of them are vertical in this situation. VV, vertical goes and vertical back. Again, we need another filter for instrument mode, Earth engine filter that's equal. Now from transmitter receiver polarization VV, we need those one in which instrument mode equals to interferometric width or IW. So, and for the next period, for the next part, we need to select one of the actually bands in the SAR data. VV and VH are two bands available in Sentinel-1, but I prefer to use same polarization data. Same polarization means the direction of electromagnetic going and back to the satellite actually are same, and in this case we will have access to more reflectance or backscatter value in the satellite data, and we can have more accurate estimation about the situation of a region of interest. So, and then in the next step, to remove the actually speckle impacts on satellite data, we need to use some sort of low pass filtering technique to remove the high pass variations in the satellite data or noises causing from the speckle impact. So using that map, I can make a function and bringing each image into as IMG, and now function returning all input images with this with the actually low pass filtering is implementing by focal mean. Here this is a mean filter that helps to reduce the impact of high pass noises or high pass signals or high frequency signals that reduces the quality of image. So the radius could be 30, And when you are using the actually low pass filtering techniques, something like focal mean or focal median, the radius is very important. For example, when you set the radius as 30, means the spatial resolution is decreasing from 10 to 30 meter, and the kernel type is a square, should be a square, and the unit will be meter, just like that. And skip the rest of the arguments. And finally, we want to have the properties of input images for the output. Now in this step, I'm gonna make a print from SAR before SAR images before flash flood to see if there is any problem uh, in this variable or not. Only two elements is available for this period of time. If you want to increase the number of images, it's very simple, just make a larger period of time. Otherwise, you can use only these two images. And remember that there is no cloud impact on the SAR data because the microwave radiation penetrates through the atmosphere, and because of the long wavelengths. And so if there is two images, meaning that these two images will be cloud free and there is no impact of cloud or atmosphere on these two satellite data. And now using map.add-layer, I can visualize these two images as a single average image to see that how the area or region of interest looks like before flood event. Map.add-layer including couple of arguments. Earth engine.object refers to the image we want to do visualization for, and here is SAR before. I'm gonna get an average because it is including two different images. Using average technique, I can join them into a single or combine them into a single image. And if they have different frames, in this case they will be merged or mosaicked same time. For the visualization parameter, leave it empty, and instead of the name we will have SAR before event, and shown should be false to avoid automatic visualization because highly reduces the speed of processing. And skip the rest of arguments, save your code and run it again. Remember to clip it based on the region of interest, clip based on the geometry, and run the code again. After a few moments, the average image will be ready. This is the SAR image before event. As you can see, there is very poor contrast in the image. Go to the setting and increase the contrast by different stretching technique available here. Here I'm gonna stretch by 90% of range of values. Click on apply, and after a few moments you can see this is the actually region of interest that's showing by SAR data. And as you can see, the darker region shows the water body, and also there are some lights in the water or dots in the water that shows the reflectance backscatter or backscatters from the ships and boats or other constructions or other existing constructions in the coastline and also in the water. And also the urban area or urban structure, as you can see, showing higher reflectance value because the SAR data or active microwave data highly sensitive to the shape of the phenomena and shape of the land covers. And as you can see, as much as when the shape of the phenomena has a little roughness, or when the roughness increases in the land covers, definitely you will see higher backscatter value here. And now I'm increasing a stretching technique by different methods to show the variations much clearly. And as you can see here, we have very high reflectance value in the urban area and also very low reflectance value in the water bodies, because the water body has a smooth surface, and also but urban area is very heterogeneous and very rough, and the roughness increases the backscatter value in this region. So after we get understanding about the situation before a flood event, now we can make another variable for after flood, or the days in which flood occurred. So now I'm gonna make another variable just same as SAR before, but this time for different dates. As you can see, you can copy and paste the previous variable with a little change here. Now here is SAR for after event. The event happened in the January or early January of 2020. For example, we can start it from the late of 2019, like this, from late of December, from 30 December to early 2020 January, for example, the third day. And also the other filter, keep the other filters same, and same also a speckling technique, because we want to compare two images for one region, and it is very important to keep everything same. And another thing is important is about the orbit path. Let me to say something about the orbit path. Here if I print the SAR for before flash flood, you can see in the properties some informations about the orbit path. And go to the properties first, and here there is some properties as orbit properties path. Here is ascending. The SAR data is available with two kind of orbit paths, ascending and descending. And remember to use the data with the same orbit path. Some of them are descending and some of them are ascending. For example, here and the ascending or descending, they have two kind of different imagery. The direction of the imagery actually is different between ascending mode and descending mode, and just it is important to filter out your data based on one of them, or ascending or descending. Here I'm gonna select both of images based on ascending. Here just you need to add a new filter in this regard. Here a new filter, create a new filter, Earth engine dot equal. Here the target property is orbit properties orbit properties path equals to ascending, and then we should have the same one. And sometimes for a region of interest, maybe only ascending or descending mode is available. No matter, you can take a print and see that which one of them is dominant, and then select one of them for the process. So here, for example, I think the ascending is dominant in this region as I checked before. So here another image is ascending. Yes, both of them are ascending, but just make sure to have access to one of them, ascending or descending mode. So, and copy, and also you must add it for the after images. It is very important when you want to compare two kind of radar data. You must use ascending or descending mode and filter your data based on. For example, you cannot compare one image from descending and another one from the ascending mode. Both of the orbit paths should be same. So here we have the same situation in the after data, but only for the days during the flash flood. And now I'm gonna make another visualization layer for the SAR after here, and instead of SAR before, we will have SAR after. Save the code and run it again. After a few moments, You can have access to new layers in the layers. This is for after events. Have a little zoom on the region of interest and increase the contrast by 90% of values in the histogram. And now, as you can see, there are there are some anomalies in the east part of the city. But if you want to see the highest water content in the urban area, you must use the minimum image. Why minimum? It is very important because the minimum uses the minimum reflectance value in each pixel, and as you can see, the water in the radar data has lowest reflectance, and when you use the minimum image, meaning that the final data reflecting the highest water content available in the region of interest. That's why it's better to use the minimum image for this region to see the highest water content for before and after events. Save the code again and run it. Now we want to do a visual comparison between before and after image to see that how the water content varies from before to after flood situation. So increase it by 90% of values again, and now this is the after image. And as you can see here, as you can see in this area, the rate of water content highly increased, and also in this area too you can see the increasing of low reflectance values that shows the area covered by the water that happened after the flood. And if you check the and also if you cross check with the references, and it is clearly shown in the references that these regions are part of flooded region. So now I want to show you how we can highlight the flooded area using a very simple equation in the Earth Engine platform. So far you learned about how to deal with the SAR data, how to do de-speckle process, and how to use how to specify different filters for the SAR data, and how to do the visualization process. And in the next step, I'm gonna make a simple equation that helps to highlight the new reflectance values or water bodies that made after the water bodies that is made after flood. So now make another variable as change map equals to now we need to calculate the minimum in the after and before images, and then compare and also then calculate the differences, or you can calculate it during your computation in the change variable. First we will have the SAR before image here, SAR before dot mean. First its mean calculated, and then subtract it from SAR after dot min. So map dot add layer, change image, clip it based on the region of interest, and leave the visualization parameter empty. Use the change and use the false at the end. Save the code and run it again. Go to the region of interest, and you can see the changed area here. As you can see, all the differences in the reflectance values highlighted here. And if you want to reduce and also it is including a lot of noises, because this is this area close to the Jakarta Bay, and that's why most of the water bodies included as a changed area, because the water reflectance value, as we expected, it is changing from one time to another time. That's why most of the water bodies included as a changed area. And there are a lot of noises for the rest of the region. In addition to the flooded area, there are a lot of noises here that we can remove them by the, for example, de-especal process that we have done before. We can change its intensity to reduce the impacts here. So now, as you can see, the changed area highlighted, but if you want to increase the contrast, you can use the stretching technique available here. And it should be noted that the positive value, the change image, ranges from positive to negative to positive values, and the positive values shows the flooded region. And now, to highlight the flooded region clearly, we need to actually set a threshold to separate the positive values from the negative values. So now I can make another variable as threshold equals to, from the change image, select those of pixels in which value is greater than, for example, 0. Definitely, if you set the 0 as a the threshold, definitely you will have a lot of noises with the flooded region. So to avoid lots of noises, it would be better to get a little distance far from 0, for example, set as 5, to reduce the amount of noises in the final images. Using map.addLayer, as you can see, the threshold.clip based on geometry. This is the change threshold. This will be a binary image including 1 and 0. The regions with 1 shows the flooded region with some noises still, and also the regions with value around with a 0 value shows actually no data. So run a code again. Now we will have a new layer as a threshold image. Now you can see most of the flooded area selected now, and but still there are a lot of noises in the final data. And then we can also make it a little bigger. I think some areas here missed, and now you can change in the region, make a change in the region of interest to cover flooded area completely, because mostly areas near to the bay covered by the water, and also as much as we get distance from the shore or coastline, the amount of the flooded area or the regions, flooded regions, highly reduced. Now it's better, looks like most of the regions were missed. And now what we can do to reduce the rest of the noises, for example, for the water bodies, the best idea is masking water body from the SAR data. That it can be done using land cover image products. Now land cover data with 10 meter spatial resolution is available in the Google Earth Engine platform. I made a video about dynamic world products in the Google Earth Engine platform. You can reach me out on my YouTube channel and find that video for the working with dynamic world product with 10 meter spatial resolution. Import it into the code as a second image collection. It is produced by Sentinel-2 data with 10 meter spatial resolution. That is one of the best products we have for the land cover mapping. Now another variable is land cover equals to second image collection. Now I'm gonna call all land covers for the 2020, the year I'm working for the flood detection, filter date for 2020 to 2021, and then filter it based on the region of interest using filter bounds. The region of interest is geometry, and the next parameter is selecting the target layer. If you go to the data description in the bands, you will see a lot of bands here, but the target band here is the label, and its value and also the water value is 0. So select the label and select the water pixels. That select allows us to select the target band that is label here, and then I'm gonna make a single land cover for the whole of year that I prefer to use the most frequent classes using that mode, and then I'm gonna select the water area using that equal 0. As I want to have water area as a 0 and the rest of classes as 1, now I need to add dot not here, and now it works better. And then after setting a threshold, use dot update mask to get rid of the water bodies, and here it is water mask. It's better. Update mask based on the water, and run the code again, and now most of the noises coming from the water bodies, permanent water bodies I mean, removed after thresholding technique. Yes, now as you can see, the permanent water body is removed, and the only thing here we have is the flooded area. And now after flooded area selected, or if you want to get a more accurate map for the permanent water bodies, you can increase the period of time you are using to produce the most frequent classes. For example, from 2018, we can set a larger time scale to find the most permanent classes actually, because the water bodies might have a lot of changes during this period of time. And now it's better, and as you can see, the only thing we have here is flooded area, but still there are some noises in the output, and these are lots of noises that coming from how do I say, speckle impact, and now we can remove or reduce their impact by increasing the radius in the low pass filters. For example, already we used 30 for the low pass filter. If I increase it to 100, although the rate of spatial resolution will decrease, but the only thing remain is related to the flood, and most of the small events and also small change or noises coming from speckles will be removed. Run a code again with a new radius value, change it to the satellite view, and check it on. And now as you can see, most of the small changes between two images removed, and the only thing remained is related to the floods, and then you can use it for further analysis. And also maybe you want to make such kind of maps to only show the areas covered by the water, and also it is very simple. For example, you want to get rid of the dark region, and maybe you want to only the flooded region. It is also very simple. Using that update mask, you can try it again. So here, make another variation for flooded area. Flooded region equals to threshold.update mask. If you update the threshold based on the threshold image, the no data value or no data pixels will be removed, and the only thing remain is the white areas. So copy and paste it here, but this time instead of the threshold we will have a flooded region, and the name is flooded region. And also we can add a color as blue here, color or palettes equals to blue. I hope it works. Let's see. Now we have a flooded region, and as you can see, the flooded maps, the flood maps or flood region is ready, and now it works very well. And if you want to increase the detail, just reduce the value of a radius. For example, if I reduce it to 60, definitely more details will be available. It's totally up to you how much of the detail you need. Check it on again, and now you can see more regions have shown. So this is a flooded area. Now if you want to calculate its area, it is also very simple task. I have mentioned a lot about how to calculate area of different parameters on my YouTube channel. You can go there and find a lot of videos about the water area calculations, and also snow area calculations, vegetation area. There are a lot of videos about the area calculation in the Earth Engine platform, and now I will explain it again for those of you who is interested to learn more. So a new variable is made. Actually, we have the final data. Just the only thing I should done is a make area image to calculate the area of each pixel in the flooded region. So the area image, area img equals to get flooded image or flood image, and then multiply it to Earth Engine.image.pixel area. Now the pixel area calculate the area of each pixel. If you want to convert it to the square kilometer, because already by default it is a square meter, if you want to change it to a square kilometer, use dot divide to 1/6 or 1 million. So after the area of each pixel calculated, now we want to get the sum of the area of flooded region. So here the final area or flood area equals to area img dot reduce region. In the selected region, I'm gonna get sum of the area for the blue region. So there are a couple of arguments here. The first is the reducer, Earth Engine.reducer.sum, because we want to get the sum of the area. Geometry or the region of interest is equals to geometry again, and then the scale will be, as the radius is 60, we need to set a scale as 60 because the spatial resolution reduced to 60. So because we wanted to reduce the impact of spatial impact on the satellite data. So, and then save it and run it again. The final unit will be based on a square kilometer, but I forgot to print it. Print flood area, run a code again. In the right panel there is a dictionary that is calculating the area of flooded region. If you had any problem in this tutorial, you can find the code link below this video on my YouTube channel, and you can compare it with yours, and then you will find the answers. So the areas covered by water is 106 square kilometer based on 60-meter spatial resolution. When you change the spatial resolution, the amount of detail will be changed, and definitely this value as the final as the estimated area will be changed based on the details you have in the satellite data. So, and now in the next step, I'm gonna highlight the precipitation values just before the flood event. As you seen before, we used from a couple of days. We used SAR data since a couple of days before the flash flood to a couple of days after the flood, and now we can also compare precipitations just for this period of time using the data with half an hour temporal resolution or GPM precipitation data. This is the main difference between this tutorial and the previous tutorial I have published on my YouTube channel. Whenever you want to study about the flood situation, it is very important to consider the precipitation data or the other important factors, because as you if you go through the articles published for the flood, there are lots of variables considered for the flood detection and also the flood studies. And it is not only limited to the precipitation or the areas covered by the flood, for example, topography, land cover, and there are a lot of things that should be considered in such kind of studies. So about the precipitation, make a new variable as PR, go to the search places and dataset and type about the GPM global precipitation measurement data is available with half an hour temporal resolution. That is awesome for the dynamic disaster or dynamic disasters or dynamic uh, uh, phenomena that happen on the earth. So precipitation equals to the third image collection. Now I'm making a filter date. It is starting from a couple of days before the flood and continues to a couple of days after flood. For example, it is starting from 2019 December, from day 25 to 2020 January day 5. So, and no need to filter bound because it is coarse spatial resolution and it has no framing structure such as we have in Sentinel-1. But the next thing is selecting the appropriate band for the precipitation monitoring. Here, as you can see, the precipitation is the target variable. It is estimating precipitation based on millimeter per hour. So select the target band using .select. The target band is selected, and now you can print precipitation values. User interface .chart .image .series. So couple of arguments we have. The first is precipitation. The region of interest is geometry. We want to get average precipitation for this region. Earth engine.reducer.mean, and then a scale will be depends on the spatial resolution. The spatial resolution is around 10 kilometer. That makes sense for the precipitation data. So the scale will be 10,000, just like that. And X properties explaining the acquisition date for precipitation data equals to system time start in the properties. After a few moments in the right panel, you can see precipitation variation with half an hour temporal frequency that is generating here. As you can see, the precipitation changes, you can see with half an hour temporal frequency ranges from 0 to 10 millimeter per hour. And as you can see in the flood event starting from the late December to early January, over this period of time, for example 1 or 2 whole days, the rate of the duration of the precipitation and the rate of the precipitation is much higher than the days before and the days after, And as it mentions in the references, the heavy precipitation in this period and its period and also the intensity of precipitation is the main important factor that caused a flood in this region. That you can see its impact and also its signs from the satellite data, whether in the precipitation data or the radar images. I hope you like this tutorial as much as I did. I tried to give you some insight about application of the remote sensing for urban flood mapping and related techniques. I hope you like this tutorial and thank you for your attention.